This video will help you with Lab 9, Ocean Acidification. The top part of the very first page shows you the whole idea behind this lab. The ocean is becoming more acidic. And the reason the ocean is becoming more acidic is because there's more carbon dioxide in the oceans. The presence of carbon dioxide lowers the pH of the ocean. And the reason the ocean has more carbon dioxide is because the atmosphere has more carbon dioxide. That atmospheric carbon dioxide is going into the ocean. We're going to look at these three different things in this lab. We're going to start on the left and look at this fact that more carbon dioxide is in the atmosphere than has ever been in the past. And I'm not just going to tell you that or make you watch videos of people telling you that. You're going to look at the data. You're going to see the real data that shows that this is true. Then we're going to look at how that carbon dioxide gets into the oceans and proof that it's there. And then we're going to look at what happens to the water that has more carbon dioxide. And the main problem is that it's dangerous for animals because animals that live in the water are accustomed to the pH being a certain level. And if the water becomes acidic, the pH changes. So let's get started. The first part asks you to do a little preliminary work by watching this 9-minute video about carbon dioxide in the atmosphere. And all you have to do is write down 3 things you learned. This is a pretty interesting video because it turns out that we started studying carbon dioxide not because we were interested in the atmospheric chemistry or the weather, but for a very different reason. So I'll let you find that out. Next, you're going to go to this website called 350.org and you're going to try to find out what these numbers mean. 275, 400, and 350, which is what the website is named. I think it'll become pretty clear pretty quickly what that number is all about. It's an international organization, and it really is an important site. Once we get past those preliminary things, you're going to read a little bit of background about someone named Charles Keeling. He was a scientist who, in 1957, decided it was probably time for someone to start actually measuring the amount of carbon dioxide levels in the atmosphere. Nobody had done that before, even though there was some concern about it. So he started making measurements, and today we have what's called the Keeling curve, a famous record of carbon dioxide values in the atmosphere as recorded by actual instruments. Now we do have records that go farther back, but those are proxies, which means they're carbon dioxide values that are recorded in tree rings or ice cores or other things. They're not direct measurements made by instruments. So there's some other things in these paragraphs that you should read because they're going to be related to questions you'll get later. But let's take a closer look at this curve. On the x-axis we have time in years. And so 1957 is when he began his measurements, and so that's when it begins. This goes only to about 2011 or 12, but I'll show you where the website is and you can go and look at the value right this instant. On the left, on the y-axis, we have carbon dioxide values in the atmosphere in parts per million. These numbers might already look a bit familiar, and that 350.org website has something to do with this 350 that's kind of missing on this graph, but this position right here on the graph. So what does this tell us? Well, this tells us the level of carbon dioxide in our atmosphere during this time period. So let's say we wanted to find the level of carbon dioxide in 1980. So we draw a line on this graph and see where it crosses this curve at 1980. And then we draw a line over to the y-axis and we see that it crosses, I'm going to say about 338 ppm. ppm is the same as parts per million. Now this is not rocket science. You don't have to be super exact, but it's definitely less than 340. It's quite a bit more than 330. I'm going to say 338. So what this means is that in 1980, the average amount of carbon dioxide in the atmosphere was about 338 parts per million. Now this is in Hawaii where his instruments were set up and are still set up today. So there's lots of variations throughout the world. The black line is the average for a given year, and the red line, you'll notice, is cyclic and seems to go up and down throughout the years. Now this has to do with some seasonal changes, and I'll just let you think about that for a moment because we will come back to it. So the first question in part A says, what is the overall trend of that black line as seen in the Keeling graph on the previous page? So basically I'm asking you, is this Keeling line increasing with time, decreasing with time, or remaining steady with time? Well, I'm going to tell you the answer because I think it's probably pretty obvious to everyone that this line is increasing with time. So that's number 1. Number 2 says, let's determine the rate of increase of carbon dioxide for each decade. In other words, is it increasing steadily or is it increasing more quickly as time goes on? Or perhaps it's increasing slower and slower as time goes on. It says we want to find the slope for each decade and compare them. Slope, if you recall from a math class, is the rise over the run. Or if you're looking on an XY graph with X points and Y points, the difference of the Y values over the difference of the X values. I'm going to show you an example and do one for you. From there, you should be able to do it on your own. I'm going to do the decade of 1970 to 1980 since we already have a data point for 1980. Okay, so here's our graph from before, and remember we already have this data point right here. Again, if you like to think in terms of XY graphs, then the coordinates for this point would be 1980, which is the X value, and 338, which is the Y value. Now I want to know the slope between this point and the point on the graph where 1970 intersects. So I'm going to draw my 1970 line. I'm going to see where it intersects over here on the y-axis. And that looks to me like it's at about halfway between 320 and 330. So I'm going to call it 325. And again, if you want to do XY points, that would be 1970, 325. Now I'm going to show you how to do it with the rise over the run for the slope. But that's what we're trying to calculate here, is this slope right here. So the rise is the difference in the y values. So I have 338 minus 325, and I get 13 ppm as my rise. And that was just the difference of the y's. The run is the difference of the x's, which is 1980 minus 1970, which is 10 years. Back to my example calculation here. The slope is the rise over the run, which for the decade I just did was 13 parts per million over 10 years, which is 1.3 parts per million per year. So I'm going to put 1.3 in there. And you're going to do the same thing for all of these other decades, and you're going to see if they're the same or different, and you're going to write the values in here. So the idea is that in this decade, on average, the carbon dioxide levels in the atmosphere increased 1.3 parts per million every year. Now you can see there's some variation in this black line, right? There's a steeper part here, less steep here, drops down here. But on average, that's the rate it increased. Did it increase at the same rate here? Will it show the same rate of increase here and here and here? That's what we're asking. Okay, so once you have that done, the next question says, what trend did you observe from the rate of atmospheric carbon dioxide increase? So we agree it's increasing, that's for sure. That was question 1. But is it increasing faster and faster? Is it accelerating? So if all of these numbers turn out to be around 1.3, then there's a steady rate of increase. It's not accelerating, it's not decelerating. If these numbers go down, let's say they go down to 0.9, 0.4, 0.3, then what that would mean would be that this curve is actually kind of flattening out like this. On the other hand, if these numbers increase to go to 1.8, 2.2, then that would imply that this curve is actually going upwards and steepening. It's hard to tell by looking at this graph because it looks fairly straight, but it isn't quite. So I'll let you figure that out and put your answer here. This question asks you to look at the graph and tell the concentration in 2010. That should be straightforward. And then you're going to go to the Keeling Curve website and you're going to find the exact value of carbon dioxide in the atmosphere today. Write today's date, the day you do this, and the value. The next page has 2 more questions related to this. And the first question here, number 6, always seems to confuse students, and I apologize, it's probably the way I wrote it. Based on your data that you've collected just so far, how many years will it take for carbon dioxide concentrations to double from today's value? So my example here is probably the problem. If today's value were 300 ppm, that's a bit silly because we just looked and we saw that today's value is not going to be anywhere near 300 ppm, right? It's probably going to be up here. So I don't know why I chose 300 ppm, except I didn't want to give you the answer. But whatever you find today's value is in the previous question. And then you decide the rate of increase is 3 ppm per year. So these two things are your choice. Where would you get 3 ppm per year? Well, that again would be from looking at this table and the trend and thinking about, well, what's this trending towards? Is it getting higher and higher? Is it getting lower and lower? Do I want to use 1.3? Do I want to use 2? So that's kind of your choice. So once you have those two numbers decided, you just take the value today, and then you calculate how many years it will take at the rate you think is going, and that's how many years it would take to double. So in the example I've given you, it would take 100 years to go to 600 ppm at the rate of 3 ppm per year. And then finally, why do scientists consider killings data to be fairly reliable? So read that first section and you'll find out an answer to that. Before I go on to the rest of this page, I want to show you something when you take a look at this data set. So this is what you're going to see when you go and you look for the answer to what today's value is. And so you can already see it's going to be somewhere around 410 to 415. But if you'll notice at the bottom, you have all these other choices. So this is 1 week of data. The gray dots are hourly averages and the darker dots are daily averages. Now you can also look at a month of data, which I've shown here. And so now you can see the hourly averages kind of vary quite a bit. Sometimes they don't vary at all. Sometimes they vary a lot. Daily averages and weekly averages. We can also choose to look at 6 months of data. Now that's looking different. If I were to look at just this, I'd say, oh, well, we're doing pretty good right now because carbon dioxide values are decreasing. That's great. Let's look at a year. Well, now we were low and then we got high and now we're going low again. So that's interesting. Let's look at 2 years. Oh, well, now we're starting to see a pattern. And this is actually that pattern that was in red on that initial map, something related to the seasons. The next questions coming up are related to this as well. And it's difficult to see on the graph that you have in your lab what month these high carbon dioxide levels and low carbon dioxide levels are related to. But it's easy to see on this graph. So just remember that these highs, when the carbon dioxide levels are highest, tend to be around May and June. And the lows tend to be around October. So just think about what's going on seasonally between May and October to make carbon dioxide levels go down, and what's going on between October and May that might make carbon dioxide levels go up. Let's look at the full record. Oh, okay, well that looks familiar. We've seen that before. What if we go to 1700 to the present? Here we have a record that includes some information since the Industrial Revolution, and so we've had a little increase. What if we go to 10,000 years ago, which has ice core data included? Look at us right here. Stay tuned to the next video. We got more to show you.